Good morning to all. So this is the e-learning. You can only see up to week 10. And here originally exam 2 was planned in week 10. Now I moved it to next week. The time setup will be pretty much similar as the first exam. And it's going to open, start on Wednesday. And the due time will be on Thursday. But I will give a little bit extended time submission window in case the student they have like a work conflict, they have work duties, so they have to do this on weekend. But the normal due time will be on Thursday by 10 p.m. Okay, that's exactly same as the first one. Whoever has any kind of a further requirement or say I need to get the extension time. So yes, you can do over the weekend, but need to send me an email, let me know what's your requirement. Otherwise, I will use the setup due time. So that's the first thing I want to announce in today's class. All right. Here is the layout strategy. We want to learn something about a process-oriented layout. So that's the thing we started. We already talked about in last class for hospital. That's very unique. Okay, and it is called a process-oriented layout. And every patient needs different treatment procedures. They need to go to different route, and which is that's the indication of the two patients A and B. They have different health problems. They need to go to different rooms and walk into different process. And for process-oriented layout, we want to arrange the work centers so as to minimize the cost of the material handling. And when you minimize this cost, we have to consider two factors. One, it is what is the load, number of material you need to handle between one room to another room, or between one department to another department. So load. And the second factor we have to consider, it is the distance you have to walk. So from one department to another department, how much distance? Because the layout is going to change the difference. Even though you have let's say we have 3 rooms over here, A, B, and C. So this is A, this is B, this is C. And so A and B, they are close together. So this is the distance probably just, let's say we all have like a 10, 10, 10. If you consider from center to center here, it is 20. And this is, if you consider center to center here, it is 10. This is from B to C is another 10. But if you lay out differently, so if you put a C over here and A over here and the B over here. Now, AB is distance is increasing, and AB's distance is increasing, but AC, their distance is decreasing. It really depends what is the load. And if your load between A and B is not really, heavier than the load from A and C. Now we can organize A and C together instead of A, B, C sequentially. So that's the two factors we have to consider. And the formula we said, it is minimize the cost equals to the 2 sigma together. 2 sigma, actually, you have the meaning behind this formula is you have to add every single travel load and so in between. If you have A, B, C, D, let's say we have A, B, C, and D. You have to consider AB, AC, and AD. So BC and BD and CD. So totally now you have 6. This is a combination problem if you only consider A to the other way. If you consider permutation, then it's going to double. So it's going to be 12 organization. So this formula gave us the idea. But how to minimize, we don't know. Okay, so unless you find out all the combinations or all the permutations, you calculate the total cost for individual layout. So this is a kind of like idea how to find out the process layout. What is the best strategy? The procedure we talked about last time is first we want to construct a from to matrix. From to is from A to B to C to D, or from like a B to C to D, or from C to D. So this is from to matrix, and determine the space requirement, and then we want to draw the initial schematic diagram to see what is the load between A, B, and C. Because if you have A, B, C, D over here, so what is the AB load? What is the AC load? What is the AD load? Then what is the load from B to C, from C to D, from the from B to D, from C to D? So this is a schematic diagram to show what is the load and corresponding to this layout, physical layout. And then from this layout and also your load, the two numbers, you can calculate what is the cost of this layout. So what is the cost? And from here you can improve. How about we change the layout? We do not use A, B, C, D. We use B, C, A, D. So you can calculate another layout to see what is the kind of cost. And then you can compare, and is the load is the cost increased or is the cost decreased? But some kind of a clue, you can figure it out. When you plan the new layout, you can think about, AB, there's a light layout, a small number of material handling need. Then I do not really care AB's distance so much. If AC, they have a very big kind of a material handling requirement, I want to make sure my A and C always put together. So that's the kind of a basic idea. This is an example of manufacturing process layout. In this overall process, they need assembly, printing, machine, and receiving, shipping, and testing. That's the 6 department or 6 procedures, you can call them. Now this is the number of loads, and they gave us the data. So some of the loads, they are 0. So there's no kind of from assembly and receiving, there's no load. You don't need to care about this, from 1 to 4. But some of the load is quite high. Okay, so as you can see over here, and from 1 and 3, this in between you have 100. And from 3 and 6, so this is the too high kind of material handling requirement. And then the rest of it is 2 and 1. So 50, 2 and 4, and here it is 4 and 5. 4 and 5 is 50. But the 20, 30, and 10, this is 20, that compare with the rest of the numbers, maybe we should focus on the 150 when you think about your layout. All right, now, and this is the initial like order. This order just the 1, 2, 3, 4, 5, 5, and 6. So, and according to the workload, we can draw the schematic like a diagram. As you can see in the beginning, okay, if you put A, B, C together, AB is 50, they are close, but AC is 100. This one, it is high. And also we are giving the cost kind of like information is if you move the material from the close together like a department, it costs $1 for each unit. But if you move a material load from one to the not close to each other, then it's going to cost $2, which is going to cost more. That means the distance will impact more. Okay, so the distance and the load you want to think about. How about if you have the setup like 1, 2, and 3. So this is the cost of $50. But if 100 mover here is $200. If you think about how about I move 1 and 3 together, then this one is going to reduce to totally $100. So it's going to cost 100. Originally, it cost 200. So it's reduced very much. And this is the cost calculation. I want you to open your e-learning. So this is the e-learning I want you to submit. And in the end of the class, all right, here I already put the layout over here. Okay, here is 1, 2, 3, 4, 5, 6, and it is the sequential order. And also I put all of the kind of like load requirement in this matrix already. So we want to calculate what is the overall cost. So if you look at this matrix over here, and 1 and 2, if they are close together, moving one material load is going to cost $1. So here it is 50 equals to this 50. Then you times kind of like 1. Or you can just say, I want to use 50, and how about we use the Excel like a table value. Here is 50 times 1. And according to this layout, this 1 and 3, they are far away, not close to each other. This costs $2 for each. So this is the load, and times 2. And here, it is 1 and 6. We look at where is 1 and 6. This is 1 and 6. So n plus 20 and times 2. N plus 30. 30 is 2 and 3. So 2 and 3, they are closer to each other, just times 1. And 50. 50 is 2 and 4. So 2 and 4. They are still, this is diagonal. We still consider them, they are adjacent. So this one, it is 2 and 4. So times 1. And 10, this is 2 and 5. So 2 and 5, they are closer to each other. So times 1. And this is 3 and 4. So 3 and 4, they are diagonal, really far away, and you times 2. And this is 100, 3 and 6, 3 and 6, they are kind of like up and down. So times 1. This is 4 and 5. 4 and 5, where is 4? So 4 and 5, they are close to each other. So this one, it is plus 4 and 5, it is 1. Do you get 570? Yes. So this is the first one. It is, and we use the sequential kind of like order and to organize all the process layout. So 1, 2, 3, 4, 5, 6. And obviously, when you use the sequential layout, you really didn't consider the high impacting factors, 100 and 100 over here. So we want to consider this high kind of like impacting load. So we want to put we want to put 3 and 1 together. And also, ideally, we can put 3 and 6 together. So another layout over here is, how about we put, instead of 1, 2, 3, we put 2, 1, 3. But for 5 and 6, 4, 5, and 6, we don't need to move to see how this looks like. So in this new kind of like highlighter, this layout, I calculated what is the cost. We still use the same kind of like a load, 1 and 2. So 1 and 2 is 50. So 50 times 1. And plus, this is 1 and 3. 1 and 3, now 1 and 3, they are really close to each other. So you times 1. And the next one is plus 20. 20, it is 1 and 6. So 1 and 6, now it is kind of like a diagonal, but they are adjacent diagonal. So it is times 1. Times 1. Okay. Plus, for this 30. 30 is 2 and 3. 2 and 3, look at this. 2 and 3. Now 2 and 3, they are really, really separated. You should times 2. So this is 30. And the next one is 2 and 4. So look at the new one, 2 and 4. That is, it is close with each other, 2 and 4. This is 50 times 1 plus, this is 10. Where is 10? It is 2 and 5. So look at 2 and 5. And this is adjacent but diagonal. So it is times 1. And the next one, it is 20. 2 and 4. So 2, this one, it is 3 and 4. So it is 3 and 4. Look at where is my 3? 3. And here is 4. So now it is the big diagonal. It is 20 times 2. And 100 is 3 and 6. 3 and 6, where is 3? Here is 6. And so you only times 1. Plus the next one, it is 50. This 50, it is 4 and 5. Look at this drawing, 4 and 5, they are adjacent to each other. So times 1. So the final result, it is in the 480. And so this is the layout of, if you consider sequence, we have how many kind of like spots, 6 spots over here, right? So if you have 6 spots, so you have so think about you have like 1, 2, 3, 4, 5, 6. If you organize them, and if you consider sequence, and the total should be so 6 times 5 times 4 times 3 and times 1. That's the total kind of like a number of permutations you can get. So this is a big number. And some of the computer program, they will provide you kind of like software. You can find out what is the minimize of this like a cost. But in our case, and we do not really use software. Instead, we use manual calculation. But we need to understand what is the mechanism behind the scene. It is in this process layout example, we really want to address the high material handling need first. So 100 and 100, that's the highest priority you want to consider to put 1 and 3 together. And then you also want to consider put 3 and 6 together. And then the next kind of like a requirement, these are the 50 and 50. So for 10, 20, and 30, they can be organized separately to be the corners, to be whatever. So, and I'm saying over here is you have so many possibilities to calculate the total cost. But there is a software can help you if you do not have software. And then for manual calculation, you want to address the highest requirement of the material handling load. So, and in this case, the second layout, it is much better than the first layout. So the cost reduction is almost $100 per week. And there's another example. So go to your Excel practice. This is and it's a job shop has 4 work areas, A, B, C, D. The distance in feet between centers of the work areas are in the left. So this is showing their relative distance from A to B, from A to C, from A to D, so on and so forth on the left. And the work piece moved in hundreds of work pieces per week between pairs of the work areas are in the right table. So it's over here. It costs $1 to move 1 piece 1 foot. And what is the weekly total material handling cost for this layout? And this, it is the distance we are given. And these numbers are the kind of like a workload we need to handle each week. They said for cost $1 to move 1 piece 1 foot. So, and for the total cost of this arrangement, so should be this one times here, and plus this times this one, plus nine and times 7 and plus 6 times this plus n times 3 plus 8 times 2 plus 10 times 6. This practice is relatively simple. They didn't ask you to rearrange the kind of like the process. Just say, okay, given this distance, given this workload, given this cost, moving per load per distance, and then find out what is the total cost. So it is 217 total. But don't forget, this is what? What is the unit is 100 pieces per week. So this is hundreds, and then actually the total material handling cost will be 21700. So you put 2 zeros over here is dollar. Mm-hmm. Okay. Yeah, 217 because it's a unit is hundreds of work pieces. That's why you add 2 zeros after your sum. So this example is quite simple because they give you the distance between A and B. They give you the load between A and B already. So all the data, they are corresponding with each other. So, and this is the material handling cost among all of the A, B, C, D process. So, and can we move to the next example? Yes, okay. This next example is a little bit kind of like twist the mind a little bit. Oh, let's see. So this is a registration at a university. So I should copy over here. And it's a registration at a university is a busy process. Students must move among different stations to complete the process, paperwork, and signatures. In the last semester's registration, as you can see, 450 went for advising, while 550 went directly to pick up the class cards, and 50 to the payment desk. So this tells us some kind of like information, okay? And they give us the kind of like data to show what is the student load. And somehow, and in this process, they gave you the distance is like this, okay? This is the table, A, B, C, D. And that's the distance between center to center is 30 feet, 30 feet, and 30 feet. And so this is the first arrangement. If we arrange the A, B, C, D sequentially, and here it is the distance, 30, 60, and 90, because A to B, it is 30. A to C is 60. And A to D, it is 90. And if you consider B to A and C to A, that's the data exactly, kind of like same as over here. We want you to find out and what is the total handling, not just saying cost, just saying the moving distance, but consider the people and the distance of the layout. And then we want to find out all of the cases like from A to B. And this is 450 times 30, right? From A to C. So A to C, 550 times A to C, the distance is 60. And then the next one, it is from A to D, so 90 distance. And then from B to A, there is a kind of like a data showing the work, showing the people's kind of like count. So 350. So we know this distance, it is 30. And how about B to C? So B to C, it is 200. And from C to D. From C to D, this is 750. And times C to D, the distance, it is 30. So here it is the total distance and the total people's count. Okay, so we can do a sum over here. So if you use the layout of A, B, C, D, now we count, this is the sum, and if you consider all of the individual, like a movement between tables. So do you get this? Do you want me to show my formula? Okay, so A to B is okay? Okay, and A to C? All right, and how about A to D? A to D is good. How about B to A? B to A, you use this. This is the people's load, and this is the distance. Actually, B to A, it is 30. Is that okay for this one? B to A. Okay. How about B to C? We look at B and C, the load, and for people count is 200. And B to C, the distance is 30. Are we okay now? So C to D. So this is the people's count movement. So 750. Now the distance is 30. Okay, here it is A, B, C, D arrangement. Do you have the final and the do you add them all up? Which one you get a different result? And you tell me, do you have ABS 135? BA is off. So if you click BA, here it is BA, the person or people's count, 350. Here is the BA is the distance, 30, right? So do we get 90,000? This is the total distance and count and the people. All right, and actually yesterday I organized them manually. If you put A, B, C, D, or like AC, BD, or like ABDC, like a manual arrangement, I have totally 24 arrangement. Mm-hmm. Yeah, somebody started from moving from A to B. So somebody stopped by from B, first stop by the B table, and then move to A. That's why they count. Yeah. Okay, what I'm showing over here is I have a totally 24 arrangement. Why I have 24? Because you think about if I'm think about here, use my pen writing on the computer screen so everybody can see it. So if you have the four kind of spots, you have four A, B, C, D a letter to put in the spots. So for the first one, I have four choices, correct? The first spot you have four choices because it's A, B, C, D now. And then for the second spot, you have three choices. And then 2 and 1. If you times them all together, this is 24. So this is a permutation problem. And in statistics, if you do permutation, you can find out, okay, the total arrangement, I can have list all of them. So A, B, C, D, A, C, D, B, B, A, C, D. So I have my paper arrangement at 24. So in this homework assignment, actually I pick up from our textbook. They said you don't need to arrange all of the 24 permutations. You just think about ways to improve the original layout A, B, C, D. So in this case, I tried kind of a couple of arrangement over here. So how about this one? We put instead of A, B, C, D, now we put A, C, D, B. Separate A and B to see how do you calculate the the total moving distance and the total count of people. So in this case, A and B, the load is what? It's people is 450, and the times the distance. What is the distance over here? A and B, it is 90. It's not 30. So you need to times this number. For A and C, so A and C is 550. So what is the distance? 30. You see, I change the layout, and then now this part is ACDB. It's ACDB. So here is 550 times AC. Did you see what my formula over here? A and C, and the people count is still 550, but AC distance now it is 30. For the next one is A and D, so people count is 50. And then A and D, that's the distance of 60. So here, 60. B and A, 350. And B and A, the distance is, it is 90. B and C, 200. B and C, B and C, is 60. So also you can consider this number, they are same. For CD, C and D, the 750. C and D, the distance it is 30, or this is 30. So this sum, you can find out, wow, very big. Okay, ACDB. I just use this as an example to show you the different layout will generate a different kind of like workload or moving load result. Which one you do not get the same result as mine? How about we start AB? You need to use the picture to help you to see which distance you need to pick up. For AC, now AC is 550. So AC distance is 30. Okay, thank you, Ward. So, can I move on to the next kind of like layout? I'm using BACD. So the first one, it is ABCD. Then there's ACDB. The third one, I'm moving around, and the table, it is BACD. So BACD, here it is BACD. So the distance is layout over here, and this people count not really change. So, and now we see what is the AB people count times the distance. So B and A, now they are close to each other, is 30. And A and C, so AC is 550, so AC is close together, so A and C, so it's 30 times 30. Can we do 80? So 80 is 50. And look at the distance A and D. So here is A and D. It is times 60. B and A, 350. So this is 30, B and A. The distance, it is 30. Can we do B and C? B and C, so it is 200 people count. And B and C, here it is 60 times B and C, it is 60. And C and D. C and D is quite big people count, 750, and then we time the distance between C and D. So C and D, this one it is 30. So we can find out the sum over here. So this one is 78,000 foot. Now we see this arrangement is a better arrangement compared with the given default or whatever you call it. So this one, the green one, so the third option, it is better. Third arrangement is better than the first one. So the third arrangement, it is B, A, C, D. And compare with the A, B, C, D one. And here is just to say the book asks us just to say, and one alternative is kind of like so the university, they find out. Okay, so provide and improve the layout and compute its movement cost. So this one, it is improve the layout. So compare with this one. So this one, it is yellow over here is 90,000, and this one it is 78,000. And also I provide a different examples. It is ACDB. Now you see layout indeed impact your movement material handling cost. And save the 3 files as one kind of like, I have this example one, 9.1 and 9.5, and save and submit this to e-learning. This one need to be counted as our in-class practice work, will be given the credit and the points. The next one we talk about work cells. So work cells is a kind of like a work layout, process layout, or kind of like you want to reorganize the people and reorganize the workforce and the machines, equipment into groups. So these rearrange the cell, only focus on one single product or a family of product groups. So for the work cell technology is kind of like from lean manufacturing and originally from the lean manufacturing, kind of like a Japanese working styles, but we found out that there are a lot of like advantages associated with work cell. Now we want to promote this technology to a lot of process, a lot of layout. So we need to use a group technology to identify what are the products that you can count them as a group of, as a family. And the main thing you want to decide is because they have similarities. And in order to use the work cell, we must justify the volume. How many pieces you are going to produce. And the cells can be reconfigured as the design or volume changes. And because everything you move the machine, you move the equipment, is going to cost. So there must be some volume to justify this reorganization is worth. Otherwise, if your volume is very small and we cannot really use this technology. So there's a justification process. There are a lot of advantages. You can name it. So the main advantage I would like to recognize it is the work-in-process inventory control. You can reduce a lot of work-in-process inventory. Another thing, it is the labor cost. Because of the cell organization, you can reduce the number of workforces needed in the cell. Originally, maybe you need 4, now reduced to be 3. And the reduction of the workforce needed, the main reason is because all of the people or the workforce, they are trained to be multitask. So they are not just focused on one machining process. They maybe are trained to taking care of this machine, also do some kind of like testing. So it's multitask workforce. That's why they can reduce their the labor cost. Some other things you can see, you can read. I will not really read one by one. And there are requirements of work cells. We need to, first of all, we need to identify what are the products. They are the family. So you can use them to produce in this in this work cell. And then I said, it's multitask workforce. That's why we need a high level of training. So they are flexible to be able to taking care of multiple steps, multiple process in the working cell. So, and also being self-contained with its own equipment and the resources. And another one, it is the poka-yoke. Have you heard this term? No? Oh, okay. Poka-yoke, it is a Japanese word. So it's also from kind of like from lean manufacturing strategies. It is a fault detection, automatically detect the fault. If you have some kind of like a design to help you to prevent the fault from happening. One example is you use jump drive, right? And then you can only plug in one way, you cannot plug in another way. So if you plug in another way, so that it, first of all, the jump drive will not work. So the computer won't read your data. And the second of all, it's going to hurt or maybe damage your the reading of from the computer chips. So that's why they have the kind of like a poka-yoke design. It is safe, and the fault plug in kind of like it's not going to happen. It's self kind of like a detection, self prevention. That's the idea of poka-yoke. And actually a lot of like daily life or things or signs that you can recognize. Oh, it is a kind of like a Pokiyoki process. And in manufacturing, the Pokiyoki process in the station or in the cell is to try to help the process automatically screen the bad parts or bad kind of like results. So that's some kind of like a requirement. Here's the example of the improved layouts using the work cell. Originally, the two-person, they didn't talk with each other. They only work on their own process, taking care of the 3 small stations. And in lean manufacturing, a lot of times they try to organize the machines in kind of like a U shape. Here, this is not a U shape, a perfect U shape, but it is kind of like a arc shape. And then they easily can interact with people together. And this with the kind of like improved space utilization, they can easily add the third people if the volume is requirement, it is bigger. So the second kind of like example, it is the line arrangement layout in the beginning. Now they totally changed this to be a kind of like a U-shaped layout. U-shaped layout. So, and these people can really easily move from one to another. So the walking distance inside the cell is reduced very much. And then originally they have 3 like a labor, now reduced to, originally have 4 work like a labor, now reduced to be 3. It is because and the small distance of the travel, they can walk from station to another station very easily. So, and train them to be able to having multiple skills to do more work. Reduce the idolization like a time. I mean, people, you don't want them to be idle. And machine, you don't want them to be idle either. So, and the next part, it is balancing, staffing and balancing work cells. So in this part, we want to first to determine what is the takt time. I think takt time also is somehow from the lean manufacturing like strategy as well. Takt time, it is the time requirement to meet a customer's volume need. So if you consider what is the total work time available and divide by the units of required to meet the customer requirements, this is produce 1 unit and how much time you used to meet the customer requirement. This is takt time. And after you determine the takt time, and then we can determine what is the number of workforces or operators needed in order to meet this kind of like a requirement. So the number of workers required or needed, we use this equation. Total operation time divided by the takt time. Then what is the total operation time? Total operation time is the entire processing time from the first step started to make the product, and after you finish this and finish the whole procedures and to get the completed product. Here is the example.
Would that also include like a maintenance that needs to be done?
I don't think so. No maintenance. I think it's just saying how much you need time, how much time you needed to from the first step and to the last step, from the raw material to the end product. It's kind of like this operation time. So this is a mirror working process. mirror, 600 mirrors per day required. And the mirror production scheduled for 8 hours per day. So the total available time, it is 8 hours. If you convert that to be minutes, 8 times 60. So 48 minutes. And the total working operations for the mirror, so I guess in this process is assembly. And then the next one, after you produce the mirror, you want to paint it to be black color or whatever the color. And then test the mirror and kind of like a quality or inspection process. And then label process. And the next one is pack for shipment. This is the total operation time from the start until the end packaging. In this process, they do not consider the maintenance of the equipment. It's totally just a count about the time used to produce this product. So if you look at this sheet, this is 50 and 40, and then 10. The next one, it is 20 and 15. You add all of the 5 procedures together, it is 140 seconds. So this is the operation time. And for takt time, the total available time is 480 minutes. And divided by 600 units, that's the customer requirement. For each part, you need 48 seconds to produce this. So this is the takt time. And total operation time, we just count all of the 5 procedures, add them up together, 140, divided by 48. This is 2.92. Because these are the people. So you cannot say, oh, we need a 2.92. So you need 3 operators in this working process in order to meet the customer requirement. So this is the staffing and the work sales. What is balancing? If you look at this chart over here, and see, we have some of the process, assembly process, you need 50 minutes. And however, the testing process, you 50 seconds. Here, for the testing process, you only need 10, 50 and 10. And that means whoever the other, if one worker is over here assembly and the next worker is testing, so the testing person can use a lot of time just drinking coffee and watch their cell phones. So a lot of idle time. So this is not the good tasking strategy. You want to make the people, all of the 3, pretty much in the same kind of working time. And this is what we call balancing. And use this balancing chart, work balance chart, and to evaluate the operation times in work cell, and to help us identify what is the bottleneck. Bottleneck is what? Is the longest time in the whole process. In the operations, if you see 50, you see 10, you see 40. Obviously, 50, it is the bottleneck. And this chart helps us to somehow you want to make this cross-trained employees can help address the labor bottlenecks. So if you have a high requirement, obviously you want to add the labor to the bottleneck station to reduce the bottleneck time. So right now it is 50 seconds. Oh, where is my chart? Yeah, here is the chart. 50 over here. And so if you see the takt time we calculate is what? it is 48 seconds. So that's why you see 50. 50 is larger than 48. And if you use one person to taking care of like a 50, and it looks like it's not enough, you need to make sure to maybe add one person somehow to rearrange this cell to make this cell to have to reduce the bottleneck time. And the next topic is to talk about a repetitive and product-oriented layout. And this one, we are going to do another kind of like in-class practice. So we do not really have enough time to talk about the details about this part. So I will just stop over here. And next time we will continue and start with repetitive and product-oriented layout and give an example to show how to and work for the layout like a strategy. How can we organize some of the procedures together as a group, and then reduce the total kind of like time to produce one piece of the part, and also increase the efficiency of the machine utilization or workstation utilization. So I will stop here.